In 1545, a doctor in Milan published a book about algebra. His name was Girolamo Cardano, and he was trying to solve a particular kind of equation, x times the quantity 10 minus x equals 40. He ground through the arithmetic and got an answer, but the answer had a problem. Buried inside, it was the square root of negative 15, which is, of course, impossible. You cannot multiply any number by itself and get a negative result. Cardano knew this. He called the experience mental torture. He wrote that the result was so subtle that it is useless and moved on. That was 477 years ago, and for most of those centuries, mathematicians agreed with Cardano. These so-called imaginary numbers were an embarrassment, a glitch in the formalism, something you occasionally bumped into and quickly swept away. Descartes called them imaginary as an insult. Leibniz called them an amphibian between being and non-being. Even Euler, arguably the greatest mathematician in history, wrote in 1770 that the square roots of negative numbers cannot be included among the possible numbers and exist only in imagination. Then, in 1926, Erwin Schrödinger wrote down an equation for how atoms behave. And right there, on the left-hand side, unavoidable, fundamental, was I, the square root of negative 1. Not as a shortcut, not as a trick you could remove at the end of the calculation. The imaginary unit is built into the structure of quantum mechanics in a way that has no classical analog. If you take a solution to Schrödinger's equation and replace Ri with its negative, you do not get another valid solution. You get the time-reversed equation. The imaginary unit is what makes probability flow forward. It is what makes the universe evolve. In 2021, a team of physicists published a paper in Nature, proving this was not a matter of convention. They designed an experiment, a Bell-type test with entanglement swapping between three parties that makes different predictions depending on whether the underlying physics uses real numbers or complex numbers. 2 independent labs confirmed it in January 2022. One used photons, the other used a superconducting quantum processor. A follow-up experiment that September ruled out the real number alternative by 5.3 standard deviations. The square root of -1, the number that does not exist, the number Cardano called useless 4 centuries ago, is woven into the fabric of physical law at the most fundamental level we can test. Schrödinger himself was uncomfortable with this. On June 6, 1926, he wrote to Hendrik Lorentz, "What is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. Psi is surely fundamentally a real function." He spent days trying to find a real valued alternative and briefly believed he had succeeded, writing to Planck that "another heavy stone has been rolled away from my heart." He had not succeeded. Within a year, complex wave functions were standard, and the square root of -1 was permanently embedded in the foundations of physics. Roger Penrose captured the irony perfectly. Then along comes quantum mechanics, and this quantum mechanics turns out to be fundamentally based on these complex numbers. They were there all the time. They have been there since the beginning of time. These numbers are embedded in the way the world works at the smallest and most basic level. Think about that for a second. Mathematicians did not invent imaginary numbers to describe physics. Cardano was solving polynomial equations. Bombelli was trying to make cubic formulas work, Euler was exploring the internal logic of algebra. None of them had any reason to think these strange objects would ever mean anything about the real world. They were playing a game with symbols. And then, centuries later, the universe turned out to be playing the same game. This is not a one-time coincidence. It has happened so many times, with so many different branches of mathematics, that one physicist called it bordering on the mysterious and said there is no rational explanation for it. His name was Eugene Wigner, and the question he raised in 1959 has haunted physics ever since. Why does mathematics, a system humans invented for abstract beauty and intellectual pleasure, keep turning out to be the language the universe is actually written in? That is the question for this video. And the honest answer, the one that most working physicists and mathematicians will give you if you push them, is that nobody knows. But the attempts to answer it, and the reasons those attempts keep failing, will take us through some of the strangest and most beautiful stories in the history of science. Let us start with Wigner himself, because the way he framed the question matters. Eugene Wigner was born in 1902 in Budapest. The son of a leather factory director, he attended the Fasori Lutheran Gymnasium, one of those schools that produced a disproportionate number of geniuses in early 20th century Hungary. The kid 1 year behind him was John von Neumann. Wigner later said, "He never felt I knew von Neumann well. Perhaps no one did. He always kept a bit apart." He acknowledged that von Neumann was a much better mathematician than I was and a better scientist, but I knew more physics. That turned out to matter. Wigner studied chemical engineering in Berlin at his father's insistence, but the physics colloquia drew him in. Every Wednesday afternoon, he sat in a room with Planck, von Lauer, Heisenberg, Nernst, and Einstein. Princeton recruited both Wigner and von Neumann in 1930. In 1939, Wigner, Leo Szilard, and Edward Teller drove to Einstein's summer home on Long Island to persuade him to write a letter to President Roosevelt, warning about the possibility of nuclear chain reactions. That letter, dated August 2nd, 1939, helped launch the Manhattan Project. During the war, Wigner worked at the Metallurgical Laboratory at the University of Chicago, helped Enrico Fermi construct the first nuclear reactor, Chicago Pile 1, and his team designed the Hanford production reactors that produced the plutonium for the Nagasaki bomb. He won the Nobel Prize in 1963 for his contributions to symmetry principles in nuclear physics. His acceptance was characteristically understated. He reportedly said, "I never expected to get my name in the newspapers without doing something wicked." But the thing that made his name famous outside physics was a lecture he delivered at New York University in 1959, the Richard Courant Lecture in Mathematical Sciences. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. It was published in Communications in Pure and Applied Mathematics in February 1960. It runs 14 pages, and it opens with a joke. A statistician shows a former classmate a paper on population trends. The classmate sees the symbol pi in the paper and asks what it means. The statistician explains it is the ratio of a circle's circumference to its diameter. The classmate protests, "Well, now you are pushing your joke too far. Surely the population has nothing to do with the circumference of the circle." Wigner confessed that this joke gave him an eerie feeling because the classmates' bewilderment betrayed only plain common sense. The essay's argument is deceptively simple. Mathematical concepts are created by mathematicians for mathematical reasons, usually aesthetic ones. Wigner defined mathematics as the science of skillful operations, with concepts and rules invented just for this purpose. The key word is invented. Mathematicians create new structures because those structures are beautiful or surprising, or because they solve problems within mathematics. They are not generally thinking about physics, but then, again and again, those very structures turn out to describe physical reality with absurd precision. He gave 3 examples. First, Newton's law of gravitation. Newton derived it from very scanty observations and could originally confirm it to about 4% accuracy. By Wigner's time, it had proved accurate to less than a 10,000th of a percent, an accuracy improvement of a factor of roughly 2,500, achieved not by refining the law, but simply by measuring more carefully. The law just kept being right. Wigner compared this situation to a man who was provided with a bunch of keys and who, having to open several doors in succession, always hit on the right key on the first or second trial. The odds of that happening by chance, he implied, are effectively 0. Second, quantum mechanics. Max Born noticed that Heisenberg's rules for calculating atomic properties were formally identical with the rules of computation with matrices, established a long time before by mathematicians. Matrices were not invented for physics. They were invented for pure mathematics. But when the matrix formulation of quantum mechanics was applied to helium, the calculated energy agreed with experiment to 1 part in 10 million. Wigner's comment on this was characteristically precise. He said, "We got something out of the equations that we did not put in." Third, quantum electrodynamics and the Lamb shift, where theory and experiment agreed to better than 1 part in 1,000. He also noted, with some reverence, that his Princeton colleague Einstein had once said he would only accept physical theories that were mathematically beautiful. Wigner called this observation the one which comes closest to an explanation for the unreasonable effectiveness. If you are willing to accept that the universe prefers beauty and that mathematical beauty is somehow the same thing as physical truth, then the mystery dissolves. But that is an enormous if. It amounts to saying the universe has aesthetic preferences, which is either a deep insight or a circular argument depending on your disposition. Now, the natural response to all of this is to say, well, of course, math describes physics. We built mathematical physics specifically to describe the physical world. Newton created calculus to solve the equations of motion. Fourier invented his analysis to understand heat flow. The tools were designed for the job. But that response misses Wigner's point entirely. His point is not that physics uses mathematics successfully. His point is that mathematics created for purely abstract reasons, with no physical application in mind, keeps showing up in physics later. And it does not just show up as a rough approximation. It shows up with 10 decimal places of accuracy. The mathematics fits the physics too perfectly, and too often, for the correspondence to be dismissed as a coincidence. And here is where the first attempt to answer the question collapses. You might say it is just luck. Mathematicians produce enormous amounts of abstract structure. Some of it, by sheer chance, will match patterns in nature. We notice the hits and ignore the misses. This is the selection bias argument, and it has serious defenders. Richard Hamming the Turing Award-winning mathematician, listed it as a partial explanation. Derek Abbott of the University of Adelaide published a paper in the Proceedings of the IEEE called The Reasonable Ineffectiveness of Mathematics, arguing that we overweight the successes, but the selection bias argument has a problem. It explains why mathematics might sometimes work. It does not explain why it works with such extraordinary precision, and it does not explain the specific pattern Wigner identified, which is that the mathematics that works best in physics is typically the mathematics that was developed for the most abstract and physics-free reasons. This is not what you would expect from random matching. If the correspondence were accidental, you would expect the best physical theories to use mathematical tools that were specifically designed for physics. Instead, again and again, the deepest physical theories turn out to need the mathematics that was developed by people who were not thinking about physics at all. Which brings us to the most dramatic example of this pattern in the history of science. On the night of May 29th, 1832, a 20-year-old in Paris sat down and wrote a letter. His name was Évariste Galois, and he had reason to believe he would be dead by morning. He was right. Galois had been a mathematical prodigy, the kind who devoured Legendre's Elements of Geometry like a novel at 15 and was solving problems that had stumped professionals for centuries by 17. The problem that consumed him was this. Everyone knew that quadratic equations could be solved with a formula. Same for cubics and quartics. But what about quintics, fifth-degree equations? Was there a general formula? Several mathematicians had proved there was not, but nobody could explain why. What made fifth-degree equations fundamentally different from fourth-degree ones? Galois' answer was revolutionary. He realized that you could associate each polynomial equation with a group of permutations of its roots. The structure of that group, its symmetry properties, determined whether the equation could be solved by radicals. He was the first person to use the word group in its modern mathematical sense. He had, in his late teens, invented what we now call group theory. But his life was a catastrophe. His father, a mayor, committed suicide in 1829 after a political smear campaign. Galois was rejected twice from the École Polytechnique, the most prestigious mathematics school in France. He submitted papers to the Academy of Sciences. Augustin Louis Cauchy apparently lost one submission. Poisson declared another incomprehensible. He was arrested multiple times for his Republican political activities, spent months in prison, and contracted cholera during an epidemic. Then came the duel. The exact circumstances remain disputed. The opponent may have been a man named Pêcheur de Herbenville, or possibly du Châtelet. The cause was almost certainly a woman. Galois himself wrote, "I beg patriots and my friends not to reproach me for dying otherwise than for my country. I die the victim of an infamous coquette." The night before, he wrote his famous letter to his friend Auguste Chevalier, summarizing his mathematical results, annotating his previous papers, and writing in the margins. Later, there will be, I hope, some people who will find it to their advantage to decipher all this mess. There is a legend popularized by E.T. Bell's Men of Mathematics in 1937 that Galois scrawled "I have not time" repeatedly in the margins as he frantically tried to capture his ideas before dawn. Tony Rothman debunked this in the American Mathematical Monthly in 1982, showing the phrase appears only once next to a particular theorem, and that Galois was mostly annotating work he had already submitted. Rothman wrote that Bell's chronology is rearranged, events are omitted, and others invented in increasing quantity, until the end of his account is largely fantasy. But the letter is real, and it is mathematically significant. The duel took place early on the morning of May 30th. Galois was shot in the abdomen, abandoned on the ground, and found by a passing farmer. He died the next day at the Hôpital Cochin. His last words to his brother Alfred were, "Ne pleure pas, Alfred. J'ai besoin de tout mon courage pour mourir, à 20 ans. Do not weep, Alfred. I need all my courage to die at 20. His papers were finally reviewed by Joseph Liouville in 1843 and published in 1846. Hermann Weyl later wrote the Galois letter. If judged by the novelty and profundity of ideas it contains, is perhaps the most substantial piece of writing in the whole literature of mankind. Now, here is the turn. Group theory, as Galois conceived it, had absolutely nothing to do with physics. It was about the internal structure of polynomial equations. It was algebra about algebra. For over a century, it developed as pure mathematics, branching into Lie groups, representation theory, and abstract algebra, driven entirely by mathematical curiosity and aesthetic taste. Then, in 1961, a physicist named Murray Gell-Mann published a paper from Caltech proposing something called the Eightfold Way. Gell-Mann was born on September 15, 1929, in Manhattan. He was a child prodigy of almost absurd precocity, teaching himself calculus at 7, entering Yale at 15, and earning his PhD from MIT at 21. He was also famously arrogant, with a talent for making sure everyone in the room knew he was the smartest person in it. But in this case, the arrogance was justified. He used a specific Lie group, SU3, to classify the bewildering zoo of subatomic particles that had been discovered in the 1950s. The particle physicists of that era had been calling their situation the particle zoo because new hadrons kept showing up in accelerator experiments and nobody could see the pattern. Gell-Mann saw it. An Israeli physicist named Yuval Ne'eman independently reached the same idea at the same time. The name was a reference to the Noble Eightfold Path of Buddhism, and Gell-Mann said it was meant to be a joke because the most common particle multiplets had 8 members. The mathematics of SU3 representation theory produces multiplets of specific sizes: 1, 3, 6, 8, 10, and so on. Known hadrons fell precisely into these patterns, but one pattern, the baryon decaplet, a triangular arrangement of 10 spin 3/2 particles, had 9 confirmed members and a hole. At the 1962 International Conference on High Energy Physics at CERN, Gell-Mann went to the blackboard and predicted the missing particle. He called it the omega minus, charge -1, strangeness -3, spin 3/2, iso spin 0, mass approximately 1680 megaelectron volts. 2 years later, at Brookhaven National Laboratory, a team of 33 physicists from Brookhaven, the University of Rochester, and Syracuse University found it. They used the alternating gradient synchrotron, which fired negatively charged kaons into an 80-inch liquid hydrogen bubble chamber. On one photograph, a particle appeared with a track roughly 2 centimeters long, and its complete decay chain was visible. The result was published in Physical Review Letters on February 24, 1964. The measured mass was 1672.45 plus or minus 0.29 mega-electron volts. The prediction had been approximately 1680. Within 0.5%, every quantum number matched exactly. The photograph became one of the most famous images in particle physics. Nicholas Samios, who was in direct charge of the experiment, would later recall the moment of recognition. The mathematics said a particle with these exact properties had to exist. The bubble chamber confirmed it. The gap between Galois' notebooks and that 2-centimeter track was 130 years. Think about what just happened. A 20-year-old in 1830s Paris, trying to understand why quintic equations cannot be solved by radicals, invented a branch of mathematics. Over 130 years later, that same mathematics predicted the existence and precise properties of a subatomic particle. Galois never heard of a proton. Gell-Mann never thought about polynomial solvability. The mathematics connected them across a century and a half, as if the abstract structure Galois discovered was already embedded in the architecture of matter, waiting to be noticed. Gell-Mann won the Nobel Prize in 1969. Galois was buried in a common grave at Montparnasse Cemetery. The exact location is unknown. He wrote in his final letter, "Preserve my memory, since fate has not given me life enough for my country to know my name." 137 years later, the entire standard model of particle physics rested on the mathematical framework he created. His country knows his name now. So the "it is just coincidence" explanation is becoming harder to sustain. But there is a second attempt to explain away the mystery, and it is more sophisticated. Maybe mathematics works in physics, because physics shaped mathematics from the beginning. Calculus was invented to describe motion. Geometry was invented to measure land. Fourier analysis was built for heat conduction. Of course, the tools fit the job. They were designed for it. This argument has real force, and Sir Michael Atiyah, who won both the Fields Medal and the Abel Prize, explored a version of it under the delightful title, "The Unreasonable Effectiveness of Physics in Mathematics." He pointed out that string theory, a physical theory, had generated mathematical conjectures in algebraic geometry that stunned the mathematicians who had been working in the field for decades. Physics returns the favor. The influence goes both ways. But this argument also breaks down when you look at the specific history. Consider what happened between 1854 and 1915. Bernhard Riemann was the son of a poor Lutheran pastor in northern Germany. Extremely shy, with a genuine phobia of public speaking, he had originally intended to study theology to please his father. But after attending Gauss's lectures at Göttingen, he switched to mathematics. To earn the right to teach at a German university, he needed to deliver a habilitation lecture. He prepared 3 possible topics and submitted them to the faculty. The tradition was for the committee to choose the first topic. Gauss, who was 76 and on the committee, chose the third. It was the one Riemann had prepared least. On June 10th, 1854, Riemann delivered "On the Hypotheses Which Lie at the Foundations of Geometry" to the faculty at Göttingen. The lecture contained no calculations whatsoever, not a single equation, only concepts. But those concepts were so deep that they redrew the map of mathematical possibility. For over 2,000 years, Euclid's fifth postulate had haunted mathematics. The first four postulates of Euclidean geometry are clean and obvious. A straight line can be drawn between any 2 points. A line segment can be extended indefinitely. A circle can be drawn with any center and radius. All right angles are equal. They feel self-evident. The fifth is different. It says, roughly, that through a point not on a given line, there is exactly one line parallel to the given line. The formal version is even clunkier. If a straight line, falling on two straight lines, makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side. It reads like a theorem, not an axiom. Euclid himself seemed uncomfortable with it. He proved 28 propositions without using it before finally invoking it for proposition 29, as if he knew something was different about it. Generation after generation tried to prove it from the other four. Proclus in the 5th century failed, unknowingly assuming an equivalent statement. Zachary in 1733 used proof by contradiction, derived actual theorems of non-Euclidean geometry, and then declared his own results repugnant to the nature of a straight line because he could not accept the conclusion. He had the answer in his hands and threw it away. Klugel in 1763 analyzed 28 separate purported proofs and concluded that every single one of them secretly assumed the thing it was trying to prove. Lambert and Legendre tried and failed. Every failure, unknown to the would-be provers, was chipping away at the most basic assumption in human geometry. 3 mathematicians figured out why independently, and the human stories behind their discoveries are as revealing as the mathematics itself. Carl Friedrich Gauss, the man many consider the greatest mathematician who ever lived, worked on the problem for over 30 years but refused to publish. In 1829, he wrote to his colleague Friedrich Bessel that he would dread the clamor of the Boeotians if he spoke out, invoking the ancient Greek shorthand for the narrow-minded. Gauss feared the philosophical backlash. In a culture where Immanuel Kant had declared Euclidean geometry an a priori truth of reason, saying the space might not be Euclidean was not just a mathematical claim. It was heresy against the foundations of epistemology. Gauss, who had spent his career earning the title Prince of Mathematicians, did not want to risk his reputation on a fight he considered beneath him. János Bolyai, a young Hungarian military officer and the son of a mathematician, had no such inhibitions. He defied his father's desperate warning. The elder Bolyai, himself a mathematician who had wasted years on the parallel postulate, had written to his son, "You must not attempt this approach to parallels. I know this way to the very end. I have traversed this bottomless night, which extinguished all light and joy in my life." This is a father begging his child not to make the same mistake he made. János ignored him. On November 3rd, 1823, he wrote back with one of the great lines in the history of ideas. "Out of nothing, I have created a strange new universe." He published his results as a 24-page appendix to his father's textbook in 1832. When Farkas sent it to Gauss, Gauss replied devastatingly that to praise it would amount to praising myself, since it matched his own unpublished work of 30 years. This crushed the younger Bolyai. He suspected plagiarism, grew bitter, and never published another mathematical work. And Nikolai Lobachevsky, working in total isolation at Kazan University in Russia, published his version in 1829 and 1830, the first published account of non-Euclidean geometry. He called it imaginary geometry, but Riemann went further than all of them. Where Bolyai, Lobachevsky, and Gauss had shown that one alternative to Euclid was consistent, Riemann conceived of an entire universe of possible geometries. He introduced the idea of an n-dimensional manifold, a space that locally resembles ordinary flat space, but can curve in any way globally. He defined what we now call the Riemannian metric, a way of measuring distances in curved space. And he showed that in 4 dimensions, the curvature of such a space requires 20 independent components to describe. Gauss, sitting in the audience, was likely the only person in the room who fully grasped what had just happened. He remarked to the physicist Wilhelm Weber that it was one of the highest works he had seen presented. Gauss died the following February. Riemann himself died of tuberculosis on July 20th, 1866, at 39 on the shores of Lake Maggiore in Italy. The lecture was not published until 1868, edited by Richard Dedekind. Here is the critical point. Riemann was not thinking about physics. He was thinking about the logical foundations of geometry. He was asking, what kinds of space are mathematically possible? That is a purely abstract question. The metric tensor, the curvature tensor, the notion of a manifold. These were answers to that abstract question. They sat in the mathematical literature for 61 years. Then Albert Einstein needed them. By 1912, Einstein had realized that gravity was not a force pulling objects through flat space. Gravity was curved space-time itself, but he did not have the mathematical tools to express this. He turned to his college friend Marcel Grossmann, a mathematician who had previously lent Einstein his lecture notes and helped him get his patent office job, and said, "Grossmann, you have got to help me, or I will go crazy." Grossmann pointed him to Riemann's work and to the tensor calculus that Ricci Cobastro and Levi Civita had developed on top of it. 3 years of struggle followed. Einstein wrote that, "Never before in my life have I been tormented by anything like this." In November 1915, he presented his final field equations of general relativity to the Prussian Academy. The metric tensor, the curvature tensor, the manifold, Riemann's entire toolkit, built for pure abstraction, turned out to be exactly what was needed to describe how mass curves space-time and how curved space-time tells mass how to move. The agreement between general relativity and observation has been confirmed to extraordinary precision, from the precession of Mercury's orbit to the detection of gravitational waves a century later. Einstein later wrote that only the genius of Riemann, solitary and uncomprehended, had already won its way by the middle of the last century to a new conception of space. He recognized that the mathematics had been there first, waiting. The French mathematical collective Bourbaki put it perfectly. Mathematics appears as a storehouse of abstract forms, they wrote, and it so happens, without our knowing why, that certain aspects of empirical reality fit themselves into these forms, as if through a kind of pre-adaptation. Pre-adaptation. That word should make you uncomfortable. because pre-adaptation implies that the mathematics was adapted to physics before the physics existed. Riemann built the tools in 1854. Einstein needed them in 1912. The tools were ready. Why? And Riemann's geometry is not even the most extreme example of this pattern. Consider Joseph Fourier, a French mathematician who was orphaned at 9, arrested twice during the French Revolution, and accompanied Napoleon to Egypt before settling down to work on what should have been a mundane problem. How does heat flow through a metal bar? In 1807, he presented his answer to the French Academy, and in 1822, he published it in full. His revolutionary claim was that any function, even a discontinuous one, even a function that jumps and zigzags, can be expressed as an infinite sum of sines and cosines. The mathematicians of his era were skeptical. Lagrange thought the claim was too broad. Fourier had to fight for years to get his work properly recognized. And the work was specifically, narrowly about heat conduction. That was the problem he was solving. Nothing else. Today, Fourier analysis is everywhere. It is the mathematical foundation of every phone call you make, because signal processing is built on decomposing complex signals into simple frequencies. It is inside every JPEG image on the internet, because image compression uses the discrete cosine transform. It is how MRI machines reconstruct images of your brain from raw frequency data. It is how Spotify analyzes the harmonics in a song. It is how crystallographers determine the structure of proteins, how quantum mechanics relates position to momentum, and how gravitational wave detectors at LIGO extract signals from noise. A tool built to understand heat in a metal bar became the mathematical backbone of modern civilization. Or consider knot theory. In 1867, Lord Kelvin proposed that atoms were knotted vortices in the luminiferous ether with different chemical elements corresponding to different types of knots. Peter Guthrie Tait spent years systematically classifying knots up to 10 crossings, trying to build what amounted to a periodic table of elements based on topology. Then, the Michelson-Morley experiment killed the ether theory, and the entire physical motivation for knot theory evaporated. It became pure mathematics with no application, studied only because the internal problems were interesting. Over a century later, biologists discovered that DNA strands literally tie themselves into knots, and that enzymes called topoisomerases cut and retie these knots to allow replication and transcription. Knot theory, developed for a theory of matter that turned out to be completely wrong, became essential for understanding the molecules that encode life. In 1988, Edward Witten connected knot invariance to quantum field theory and won the Fields Medal. Today, topological quantum computing encodes information in braided structures that are mathematically described by the same theory Tait developed to catalog non-existent ether vortices. Every one of these stories has the same structure. Mathematics developed for purely abstract reasons, or for physical reasons that turned out to be wrong, surfaces decades or centuries later as the precise language for describing something real, and every one of them makes the selection bias argument harder to sustain. We are not cherry-picking a few lucky coincidences from a vast landscape of failures. We are looking at a systematic pattern in which the most beautiful and abstract mathematics turns out again and again to be the most physically relevant. So we are now two failed explanations deep. It is not just coincidence, because the pattern repeats too consistently and too precisely. It is not just that physics shaped mathematics, because the mathematics that turns out to be most useful is specifically the mathematics that was not shaped by physics. Where does that leave us? There is a third attempt, and it comes from the people who study the foundations of mathematics itself. The idea is simple. Maybe mathematics is not something humans invent. Maybe it is something we discover. Maybe mathematical structures exist independently of human minds. And when we do mathematics, we are exploring a landscape that is already there. This is called mathematical Platonism, and it has been the default position of many of the greatest mathematicians in history. It traces back to Plato's theory of forms, the idea that abstract entities like numbers, geometric shapes, and mathematical relations are eternal, unchanging, and independent of the physical world. Plato built on Pythagoras, who believed the world was, as Mario Livio puts it, quite literally generated by numbers. Kurt Godel, arguably the most important logician since Aristotle, was a committed Platonist. In 1964, he wrote, "We do have something like a perception also of the objects of set theory, as is seen from the fact that the axioms force themselves upon us as being true. I do not see any reason why we should have less confidence in this kind of perception, that is, in mathematical intuition, than in sense perception." His incompleteness theorems, published in 1931, arguably support this view. The story of how they came about is itself a testament to mathematical independence from human wishes. David Hilbert, the towering figure of early 20th century mathematics, had launched an ambitious program to put all of mathematics on a firm foundation. His formalism treated mathematics as a game of symbol manipulation, much more akin to a game, bringing with it no more commitment to an ontology of objects or properties than Ludo or chess. He wanted to prove, from within mathematics itself, that the system was consistent, that it could never produce a contradiction, and that every true statement could eventually be proved. It was a grand, optimistic vision. Mathematics would be made safe. Godel destroyed it. He proved that in any consistent formal system powerful enough to encode basic arithmetic, there are true statements that the system cannot prove. The Godel sentence is true. You can see that it is true, but no amount of mechanical deduction within the system will ever produce it. This was not a minor technical limitation. It meant that mathematical truth is fundamentally bigger than any formal system we can construct. No matter how many axioms you add, no matter how cleverly you set up the rules, there will always be truths that escape the net. The Brouwer-Hilbert controversy of the 1920s, which had grown so fierce that Hilbert had Brouwer removed from the editorial board of the journal Mathematische Annalen, was rendered moot by a 25-year-old Austrian logician who showed that neither side had the full picture. If you are a Platonist, Godel's theorems are the strongest evidence for your view. They suggest that mathematical truths exist independently of our axiom systems. Truth is out there, whether or not we can prove it. Godel himself drew this conclusion explicitly. Roger Penrose, the Nobel laureate, takes this further with what he calls the three worlds framework. There is the Platonic mathematical world, the physical world, and the mental world. Each is somehow founded in the previous one. Mathematical laws govern the physical world. The physical world gives rise to conscious minds, and conscious minds somehow access mathematical truth. Three deep mysteries connect them, and we do not understand any of the three connections. Penrose writes, "I like to think that, in a sense, the Platonic world may be the most primitive of the three, since mathematics is a kind of necessity, virtually conjuring its very self into existence." Max Tegmark, the MIT physicist, takes this to its logical extreme. His mathematical universe hypothesis, published in Foundations of Physics in 2007 and popularized in his book, Our Mathematical Universe, in 2014, makes a staggering claim. He does not say the universe is described by mathematics. He says the universe is mathematics. His argument is that if external reality exists independently of humans, then a complete description of it must be free of any human-dependent concepts. A description with no human baggage is precisely a mathematical structure. Therefore, physical reality is a mathematical structure. He goes further. His level 4 multiverse proposes that all mathematical structures exist physically. Every consistent set of equations describes an actual universe somewhere, but even Tegmark's radical position does not really answer Wigner's question. It just pushes it back a step. If the universe is a mathematical structure, why is it this particular mathematical structure? Why these equations and not others? And if all mathematical structures exist, then we are back to an anthropic argument. We observe this mathematics because only this mathematics produces observers, which explains nothing about why mathematics and physics are linked in the first place. Meanwhile, the anti-Platonists have their own problems. Hilbert's formalism was demolished by Godel's theorems. If mathematics is just a game with formal rules, then you cannot even prove the game is consistent from within its own rules. The game keeps producing truths that the game cannot contain. The Israeli-American astrophysicist Mario Livio surveyed the entire battlefield in his book Is God a Mathematician in 2009 and concluded with admirable honesty that mathematics is both invented and discovered. "I believe that we invent the concepts," he wrote, "but then we discover all the relations, all the theorems around these concepts. We chose to define prime numbers, but the fact that there are infinitely many of them, or that they distribute themselves along the number line according to a specific logarithmic pattern, or that they connect to the zeros of the Riemann zeta function, none of that was our choice. We stumbled into it. This is elegant, but it does not resolve the mystery either, because the question remains, why do the relations we discover in abstract mathematics keep matching the relations we observe in physical reality? Livio's answer accounts for the internal richness of mathematics. It does not explain the external correspondence. Every attempt to answer Wigner's question either fails outright or transforms into a deeper version of the same question. The mystery does not dissolve, it escalates. And perhaps the person who understood this escalation most viscerally was someone who had no formal training, no university education, and no contact with the Western mathematical establishment until he was 25. Srinivasa Ramanujan was born on December the 22nd, 1887, in Erode, Tamil Nadu, to a devout Brahmin family. His formal mathematical education consisted of one book. At 15 or 16, he got hold of George Shoebridge Carr's Synopsis of Elementary Results in Pure and Applied Mathematics, a compendium of roughly 5,000 theorems, presented with minimal proofs. Ramanujan did not just read it. He verified every result, and then he went beyond it, far beyond it. Paper was expensive, so he worked on a slate, transferring only his final results to notebooks. 3 notebooks, over 600 pages, containing nearly 3,900 results, almost all without proofs. On January 16th, 1913, he wrote a letter to G. H. Hardy at Cambridge. It opened, "Dear Sir, I beg to introduce myself to you as a clerk in the accounts department of the Port Trust Office at Madras on a salary of only £20 per annum." The letter contained roughly 120 theorems. Hardy's initial reaction was suspicion. This had to be a fraud. But something stopped him. He showed the theorems to his colleague Littlewood. His later recollection is famous. "I had never seen anything in the least like them before. A single look at them is enough to show they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have the imagination to invent them." Think about that last line. Hardy, a man who spent his life studying proofs and formal verification, was saying that the theorems authenticated themselves. Their beauty was evidence of their truth. This is exactly the kind of thing that is not supposed to happen if mathematics is a human invention. If we made it up, then a brilliant hoaxer could invent convincing false theorems. But Hardy was claiming that the real ones have a quality that the false ones could never have, as if they were discovered, not invented, as if Ramanujan had found them rather than created them. Ramanujan himself had no doubt about this. A devout Hindu, he attributed his mathematical inspiration to the goddess Namagiri, his family deity. He described visions of mathematical formulas appearing on a screen of flowing blood. When Hardy invited him to Cambridge, his mother initially refused on religious grounds. Crossing the ocean was sinful for a Brahmin. She relented after Namagiri appeared to her in a dream ordering her not to stand in the way. He arrived in England in April 1914, a strict vegetarian in wartime Britain, and his health deteriorated steadily. The English climate, the food, the isolation from his family and religious community, the grinding culture shock of Edwardian Cambridge, all of it wore him down. But his mathematical output was staggering. He and Hardy published paper after paper, with Hardy providing the rigor and Ramanujan providing the vision. Hardy later wrote that Ramanujan's formulas had a quality of inevitable rightness, as if they could not have been otherwise. The famous taxicab story captures something about how his mind worked. Hardy visited him at a nursing home in Putney and remarked that his cab number, 1729, seemed to be rather a dull one. Ramanujan replied instantly, "No, it is a very interesting number. It is the smallest number expressible as the sum of 2 cubes in 2 different ways. 1 cubed plus 12 cubed, 9 cubed plus 10 cubed." He did not calculate this. He recognized it the way you might recognize a face. The number 1729 is now called the Hardy-Ramanujan number, and taxicab numbers are an entire category of mathematics named after this conversation. Hardy rated mathematical talent on a scale. Himself, 25. Littlewood, 30. Hilbert, 80. Ramanujan, 100. Asked what his greatest contribution to mathematics was, Hardy unhesitatingly replied that it was the discovery of Ramanujan. He called their collaboration the one romantic incident in my life. Ramanujan died on April the 26th, 1920, at 32. His health had never recovered from the years in England. His last letter to Hardy, written in January 1920, introduced what he called mock theta functions, objects whose full significance would not be understood for decades. They turned out to be connected to black hole entropy, string theory partition functions, and deep questions in number theory that are still active research areas today. In 1976, the mathematician George Andrews was searching through a box of papers belonging to the late G.N. Watson at the Wren Library in Trinity College, Cambridge. Inside, he found 138 loose pages in Ramanujan's handwriting, containing over 600 formulas, none of which had ever been published. The pages had sat there for decades. By one account, they had nearly been incinerated years earlier. Bruce Berndt compared their discovery to finding Beethoven's 10th Symphony. Andrews and Berndt spent the next 40 years proving the claims in what became known as Ramanujan's Lost Notebook, publishing a 5-volume series between 2005 and 2018. Every claim checked out. Here is what is haunting about Ramanujan's story. In the context of Wigner's question, many of Ramanujan's results, produced by a self-taught clerk in Madras, guided by visions of a Hindu goddess, turned out decades later to be relevant to black hole physics, string theory, and statistical mechanics. He was not doing physics. He was not even doing mathematics in the way his Western contemporaries understood it. He was receiving formulas, testing them, and writing them down. And those formulas described aspects of reality that nobody in 1915 could have possibly anticipated. If mathematics is a human invention, what was Ramanujan inventing? And if it is a discovery, what was he discovering, and how? We have one more case to examine before we close, because it illustrates something the others do not. The imaginary numbers story, Galois and group theory, Riemann and space-time. These are all cases where mathematics preceded physics by decades or centuries. But there is also a case where mathematics and physics arrived simultaneously, and the result was just as unsettling. In January 1928, Paul Dirac, a physicist whose personality was as unusual as his equations, published The Quantum Theory of the Electron. Dirac had grown up in Bristol under a father who insisted Paul speak only French at dinner. If Paul made a grammatical error, his father would refuse his next request. Paul ate alone with his father in the dining room, while his mother and siblings ate in the kitchen. As a result, he often vomited at the table because his father would not allow him to leave it. He learned to minimize mistakes by minimizing words, and he carried this habit for the rest of his life. His Cambridge colleagues defined a Dirac as a unit of speech equal to 1 word per hour. When someone at a lecture said, "I do not understand the equation on the top right-hand corner of the blackboard," Dirac waited through a long silence and replied, "That was not a question, it was a comment." When he first met Richard Feynman, he said, "I have an equation. Do you have one too?" But his equation was extraordinary. He had set out to reconcile quantum mechanics with special relativity for the electron, and the equation he found had 4 components. 2 of them described the electron as expected, The other two described something with the same mass but opposite charge. At first, Dirac tried to identify these extra solutions with the proton, but the mathematics would not allow it. The masses had to be equal. In 1931, he bit the bullet and predicted a new particle, an anti-electron, identical to the electron in every way except for having positive charge. On August 2nd, 1932, Carl Anderson at Caltech photographed the track of this exact particle in a cloud chamber, a 63 mega-electron volt positron, curving the wrong way through a magnetic field. Anderson was initially unaware of Dirac's prediction. The discovery was independent. A physicist wrote an equation for beauty and mathematical consistency, and reality answered. Now, before we go further, there is a common misconception worth correcting here. You will sometimes hear people say that mathematics describes everything in nature, that the golden ratio appears in seashells and galaxies and the proportions of the human face, that the Fibonacci sequence is a universal code written into biology. This is substantially overstated. George Markowski wrote in the College Mathematics Journal in 1992, "It would take a large book to document all the misinformation about the golden ratio. The Nautilus shell, perhaps the most iconic claimed example, is a logarithmic spiral, but its expansion rate does not match the golden ratio. Many claimed instances reflect confirmation bias. If you go measuring things looking for a specific ratio, you will find something close to it, because any ratio between about 1.5 and 1.7 will look like a hit. Fibonacci numbers do genuinely appear in plant phyllotaxis. Sunflower seed heads spiral in counts of consecutive Fibonacci numbers, 34 and 55, or 55 and 89, because growth following the golden angle of roughly 137.5 degrees produces optimal packing. That is real. But the broader claim that the golden ratio is a universal design principle woven into nature, art, and the human body is not supported by evidence. The actual cases where mathematics describes nature with extraordinary precision, the cases Wigner was pointing to, are far stranger and far more specific than golden ratio numerology. They involve abstract structures with no obvious connection to nature at all. Dirac later said, "I think there is a moral to this story, namely that it is more important to have beauty in one's equations than to have them fit experiment." And even more provocatively, one could perhaps describe the situation by saying that God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. Freeman Dyson said of Dirac, "His discoveries were like exquisitely carved statues falling out of the sky, one after another. He seemed to be able to conjure laws of nature from pure thought." Dirac won the Nobel Prize in 1933 at 31. He seriously considered declining it. Rutherford advised him that a refusal will get you more publicity. A London newspaper called the young laureate as shy as a gazelle and as modest as a Victorian maid. He brought his mother to Stockholm, but excluded his father. His personal life eventually transformed. In 1934, at a restaurant in Princeton, Eugene Wigner introduced his sister Margit to the frail, quiet physicist at the next table. Margit spotted, as she later described it, a frail, lost-looking young man, and asked her brother who he was. Wigner replied, "Why, that is Paul Dirac, one of last year's Nobel laureates." She asked to invite him over. They married in January 1937, the same year Wigner's first wife Amelia died. The marriage softened Dirac. When Margit complained he never answered her letters, he drew up a table with her questions in one column and his answers in another. But eventually he wrote to her, "Mansi, my darling, you are very dear to me. You have made a wonderful alteration in my life. You have made me human." After his father Charles died, Dirac wrote, "I feel much freer now, and I am my own man." The connection between these two men, Wigner and Dirac, is too perfect to be scripted. The physicist who asked why mathematics describes reality married his sister to the physicist whose equation proved it most dramatically. They were family, and neither of them could answer the question. So where does all of this leave us? We have the imaginary numbers, invented by algebraists in the 1500s and proven necessary for quantum mechanics in the 21st century. We have group theory, invented by a doomed 20-year-old to solve polynomial equations and used 130 years later to predict subatomic particles. We have Riemannian geometry, invented as pure abstraction and needed 61 years later to describe the curvature of space-time. We have the Dirac equation, written for mathematical beauty and revealing the existence of antimatter, and we have the failed explanations. It is not coincidence, because it happens too often and too precisely. It is not that physics shaped the mathematics, because the relevant mathematics was developed independently. Mathematical Platonism says the structures exist independently, but does not explain why physical reality conforms to them. Formalism says mathematics is a game, but Godel proved the game is not self-contained. Tegmark says reality is mathematics, but that does not explain why this mathematics and not some other. Livio says we invent concepts and discover relations, but does not explain why the discovered relations match physical law. The skeptics make fair points too. Mathematics fails spectacularly in some domains. Turbulence remains unsolved. The Navier-Stokes existence and smoothness problem is one of the 7 Clay Millennium Prize problems, announced in 2000, carrying a $1 million prize, and nobody has cracked it. There is a quote attributed to Heisenberg. "When I meet God, I'm going to ask him 2 questions. Why relativity and why turbulence? I really believe he will have an answer for the first." Consciousness defies mathematical formalization. David Chalmers formulated the hard problem of consciousness in 1996, and it remains completely beyond mathematical reach. Economics suffered catastrophic mathematical failures in the 2008 financial crisis, with sophisticated models dramatically underestimating systemic risk. Weather prediction hits chaos theory's wall after about 10 days. And there is a deeper evolutionary argument. Richard Hamming pointed out in 1980 that we have been selected to fit the environment. Our brains evolved to detect patterns because pattern detection helps you survive. Finding mathematical regularities in nature might say more about our cognitive architecture than about the universe itself. The physicist Brandon Carter formalized a version of this in 1974 with the weak anthropic principle. We can only observe a universe compatible with observers. A universe without mathematical regularities might not produce brains capable of doing mathematics. So of course, we find ourselves in a mathematical universe. We could not find ourselves anywhere else. The philosopher Mark Steiner, In his 1998 book, The Applicability of Mathematics as a Philosophical Problem, attacked this from another angle. He argued that the real puzzle is not just that mathematics works, it is that specifically human aesthetic preferences in mathematics, our sense of beauty, elegance, and symmetry, turn out to track physical truth. Physicists do not just use any mathematics. They use the mathematics they find beautiful. And this beauty-guided strategy works, which means either the universe is, in Steiner's phrase, user-friendly to human cognition in a way that demands explanation, or there is something deeply anthropocentric about the whole enterprise that naturalism cannot account for. The counter-argument, pressed by Jesper Lutzen in 2011, is that mathematical aesthetics were shaped by physics from the start. We find certain mathematical structures beautiful because our mathematical sense co-evolved with our physical intuitions. The beauty is not independent of the physics. It is a reflection of it, which, if you follow the logic, means that the evolutionary argument and the mystery argument might both be partly right. Our brains evolved to find mathematical patterns, but the universe had to contain those patterns for the evolution to work. You can explain the lock or the key, but the fit between them remains strange. But notice something about these failures. Turbulence, consciousness, economics, weather, these are all complex systems with enormous numbers of interacting components. At the fundamental level, the level of individual particles and space-time geometry and quantum fields, mathematics does not fail. It succeeds to 10, 12, 14 decimal places. The failures live at the level of emergent complexity. The successes live at the level of fundamental law, which means the mystery is not just that mathematics works. It is that mathematics works exactly where you would expect it to, if mathematics was somehow built into the foundation of reality itself. Wigner ended his essay with a passage that has been quoted more than perhaps any other in the philosophy of science. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend, for better or for worse, to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. He called it a miracle. He said, we do not understand it. He said, we do not deserve it. And 66 years later, after all the philosophy and all the experiments and all the arguments, the honest answer is the same. We still do not understand it. Every explanation we have either fails on its own terms or mutates into a restatement of the original mystery. But maybe that is the point. Maybe the deepest questions are not the ones with answers. Maybe the deepest questions are the ones that keep pulling you further in, that keep refusing to close, that stay open no matter how many brilliant people throw themselves at them. In 1959, a Hungarian physicist stood up in New York and asked why the universe speaks mathematics. A 20-year-old in Paris had given part of the answer 127 years earlier without knowing it. A self-taught clerk in Madras had given another part, guided by a goddess. A shy pastor's son in Göttingen had given another, in a lecture without a single equation. A taciturn Englishman in Cambridge had given another, in an equation with 4 components and too many solutions. None of them answered the question, all of them deepened it. And the fact that the question keeps deepening, that every new piece of mathematics that describes reality makes the correspondence more precise and more mysterious, not less, may itself be the most important clue we have. There is one final detail worth noting. Eugene Wigner died on January 1st, 1995, in Princeton at age 92. Paul Dirac had died in 1984 in Tallahassee, Florida. Galois was buried in 1832, Riemann in 1866, Ramanujan in 1920. The human beings who encountered this mystery, who felt it in their bones, who tried to articulate it or simply produce the evidence for it, are all gone. Their equations remain. And the equations still work. Whatever it is that connects abstract mathematics to physical reality, it operated before any of these people were born, and it continues to operate after they died. It does not need us. It may not even notice us. But somehow, improbably, we can see it. Wigner was right. It is unreasonable. It is a gift. And we do not understand it. But we are grateful, and we keep looking.